That's fantastic. So yeah, so Guilherme is going to talk about COLA, beyond-LCDM models, and photometric probes. But I want to make an announcement. So Nick is not feeling very well. So if he doesn't come to the talk in the afternoon, he's okay. Then I think we can have the discussion on fast simulations and not so fast simulations. Not so EFT, Henrique. Is that okay? So we do it at 2 if need.
We're back at 2 for the discussion.
Yeah, because it's very possible that Nick will not be able to give his talk.
Okay, no worries.
So we do the discussion too, and then we're free. Is that okay? Okay. So Guilherme, please go ahead.
Yeah. So thanks, Rogério, for the introduction and also the invite. So after Hugo's talk, I'm kind of like I don't know, we're talking about real stuff and real things, and now I'm going to talk maybe about like beyond-LCDM models, which are normally not well, things are already hard for lambda-CDM, and beyond-LCDM models, they're even harder. And so sometimes it may seem a little bit fringe or like off topic, but I'll try to mix everything together. Also, I'm going to talk about a certain method that is called COLA, but it's just also something I'm going to discuss that not necessarily this is the way forward. And the last one I put just because I talk about cosmic shear, but I'm not an expert on that. I think the people here are way better and way more understanding on this topic than myself. So it's going to be good for the conversations that we are going to have. So, yeah. So our universe so far, we all know, basically this introduction is going to be a little bit too much for like not too much, but a little bit talking again. So the universe that we know so far is lambda-CDM. So we know that the general relativity is a law description, and it's one of the pillars of the lambda-CDM model, where the gravitational interaction is solely given by the Einstein field equations. So G mu here, the capital G mu capture everything that we need to know about gravity. Lambda is what causes the current acceleration expansion. And on the right-hand side, we have the energy momentum tensor of all other matter species. So I may ask, and people often ask, is why we look for beyond-LCDM theories. So there is this old problem of the cosmological constant problem, in which we have orders of magnitude between the infer value on the theoretical side using quantum field theory methods, and the one that we observe in the universe for the vacuum density. So the two of them are orders of magnitude different. We have these so-called cosmological tensions, where we know that one of the biggest ones are this Hubble constant over time, so the H0 tension. We can see that the way we measure it using Cepheids and the tip of the red giant branch is the values are very different from the one that we inferred using the CMB. And also there is this new results from DESI, which are like, they come from April, which just show that there is a mild preference for an evolving dark energy in the universe rather than lambda-CDM. So basically W is not -1, but then it's going to be a simple Taylor expansion that captures some of the physics. So basically there's going to be the W0, and the first time derivative will be WA. So the value changes when we add different sets of supernova data sets. So in the end, we can see that different data sets, they're different in the sense that not only the way they were, the supernova, they were detected, but also on the way that they use the light curve fitting algorithms and so on and so forth. So this is not something I'm going to talk about more, but I'm just going to mention here that this is one of the things that people often use as a motivation to look for beyond-LCDM models. Of course, there's also the stress tests of the concordance model, which is lambda-CDM, and cosmological tests of gravity. So far, we don't have very good constraints on gravity in the cosmological scales. So basically, with the stage 4 LSS surveys that are coming, we hope that we can even do better than we have so far. So there's also some of the new results from DESI that I'm going to briefly talk about. So our universe is, of course, at large scales, is homogeneous and isotropic. This is the cosmological principle. And the success of this description gives us a perfect knowledge of what is on the background of cosmology. So basically geometry. We're very good at, not very good, but this is a very easy way to compute and generate predictions for different theories using the background cosmology. We impose homogeneity and isotropy in Einstein field equations, and we are left with the Friedmann-Robertson-Walker metric. And when we impose the same thing on the matter content, we are left with just a diagonal energy momentum tensor, where the first component, the 0, 0, is the energy density of the matter species, and the spatial part is just the isotropic pressure. So at the background level, these two quantities, the pressure and the energy density, they're tied together by the equation of state parameter, okay? And for different species, this equation of state parameter may evolve or not. So for CDM, is 0, for instance, because it's non-relativistic pressure. And for instance, for massless neutrinos and radiation, which is photon, it's just 1/3. For massive neutrinos, it's a little bit tricky, but we can accurately also compute them nowadays using very different methods. One of them is using Einstein-Boltzmann solvers. So the whole equations that we need to solve then for the background is just these two, which are the Friedmann equations. The first one is a constraint equation, and the second one is a dynamical equation, okay? And they govern our homogeneous and isotropic background, okay? So far also, we have relied on the very simple description of, not so far, but before stage 4 LSS surveys and the whole effort that came with it. We used to rely on initial small fluctuations that we see from the CMB, and we evolved them linearly as well. So this was very successful, not only to extract constraints from the CMB using the Planck data and other telescopes as well, like ACT and SPT. And this is a very interesting way to describe the universe, but rather simple, because we know that the gravitational collapse is not linear. So this simplistic description here needs to be revised in order for us to provide the best methodology to extract constraints from the data to come, okay? And there you go. This is basically what we had. So this was the success that we had that led to the Einstein-Boltzmann solvers that we now have nowadays. For instance, CAM, CLASS, and yeah, I think that that's basically it. So also, we started our investigation of using some structure information from previous years from SDSS and so on. We started using the same codes that we have. For instance, we modify them to expand from just general relativity to more general theories, for instance, modified gravity, interacting dark energy, and mainly because these codes, since the universe is expanding linearly in these codes, we can compute and generate accurate predictions for the linear matter power spectrum. So basically, the 2-point correlation function in real space, it's just the Fourier transform of the matter power spectrum that we can generate from using these codes. And here is just an example of what we have at linear order. So basically this, I'm just showing different masses of the neutrino species, 0.1, 0.2, 0.3 electron volts. And we can see how each of these theories, so each of these models, they impact the matter power spectrum as well as the 2-point correlation function in real space. But when we go to beyond linear theory, so this plot here I'm showing, it's just using a very simplistic prescription for the nonlinear matter power spectrum, which is just basically the halo fit prescription. We can see that at small scales, we see an enhancement that is precisely given by the collapse of structure, so collapse of matter. And we can see that the same imprints that we have in the nonlinear matter power spectrum are also translated to the correlation function. Okay, so this is more or less where we are and where we need to do better for beyond lambda CDM models. I'm showing here just massive neutrinos and playing with the sum, because this is something that is more easily for everyone to understand, rather than to just jump ahead and already discuss modified gravity or something like that. So what also we need to do? So for stage 3 surveys, the collaborations use these old fitting formulae that were very successful. So for instance, one of these prescriptions is called the HM code. And we can see here that when we compare this old prescription with respect to the stage 4 counterpart, which is the Euclid emulator 2, we can see that there is a lot of deviations precisely around the BAO scale. This is due to many things, but we can see that for stage 3, we were not yet at the level of precision requirements that we needed to do to have everything in agreement. So basically, we can see that the BAO scales, we have different peaks, and also at small scales, we have different scale dependencies, which are also inherent, they are inherited from different codes and so on. So the error bars were simply too large to see that these codes were not in agreement with each other.
So what's the problem with Euclid emulator or?
So yes, so the reference one is the Euclid emulator 2, and the one that they're varying there is the HM code. So it's just a parametric formula that it's calibrated using hydro simulations. So
It's 6%.
yeah. So, but this is that's the thing. Like this is what I want to talk about, and that's why that's a good question. So this is the comparison that I did in Euclid emulator 2 paper, and this difference may seem very big, precisely because it's 6% already at z equals 0, but this difference may not be purely physical, because the way Euclid emulator 2 samples the simulations that they use to calibrate this matters a lot, precisely in the BAO scale. So how you estimate the power spectrum also comes into play of what you want to understand. So basically, of course, if you see the Euclid emulator 2 paper, you're going to be biased and see that and think that the HM code is doing very badly. But maybe this is not the case. We don't have all the access and all of the understanding of how the collaboration did the K-binning. So basically, this is also something that comes at play. And yes, this is one of the things that we need to deal with in for stage 4 LSS surveys. So this is also a nice plot that I took from the methodology, the multi-probe modeling strategy and validation, which shows that basically when you have different prescriptions, so you have Cosmic MU, Euclid emulator, HM code, and the baseline, which was HaloFit, you see that the ellipses were not shifted by a lot, even though they had a very big error bar difference between each other. They were already at 6%, but you can see that the survey was still not accurate enough and precise enough to see that, okay, all of these different methods are going to be biased among each other.
It depends on scale cuts, of course.
This depends on scale cut, but it's mainly like so the scale cuts should be
the scale cuts.
the scale cuts of that should be around here. So this is 0.2. So this difference is already like very prominent at the BAO scales. So this is more or less of what I'm talking about. So there is a very big dependence on how we do and measure all of these things. But as I said, we need to increase the modeling for stage 4 galaxy surveys, as DESI, Euclid, and LSST, due to the increase in constraining powers coming from them. One of the things that I have already mentioned is the preference for this evolution of the dark energy equation of state, which is just captured by this plot over here. We can see that it's way far off from what we expect from lambda CDM, which would be the dashed lines over there. Also, the same preference that was shown in terms of the BAO, which is just basically geometry and testing distances. At the level of the structure of growth, there's still preference for an evolving dark energy remained. So here on the right-hand side here, it's the same plot from before, but now using a different modified gravity theory. So basically, while in the level of the background, we can just parameterize the equation of state parameter. When we go to linear perturbation theory, the same is not true. So we need some weird predictions for how structure grow, so how the structures have grown in the universe in terms of two phenomenological functions. Basically, we have that mu function over there that can be just a time-dependent function or a scale-dependent function, and this sigma function over there. The first one will of course affect how matter collapsed, because it's directly the one that comes from the Poisson equation. And the second one comes from due to the presence of some modified gravity theories exhibiting anisotropic stress. So basically, both of these gravitational potentials, psi and phi, they're not going to be one. So in general relativity, they're simply one. They're the same thing. But in modified gravity, they may not be the same thing. However, DESI have found, of course, that there's no evidence of deviation from general relativity, and at the background level, we still favor the beyond-LCDM. So I just want to stress as well that for the DESI analysis, they follow the same analysis that they did for their paper 7, which was for general relativity, which was using a perturbative template, which is basically something that may be discussed later today in the meeting and the discussions that Rogério has said. This is not a template that was used and calibrated using simulations. Well, it was calibrated using simulations, but it's not something that comes directly from the output of these simulations.
They also have to cut scales, right? Because they're using linear perturbation theory
So
for the modified gravity, especially.
So for the modified gravity, they also used linear, and they also use different things. For instance, they use the same kernels that we use for general relativity. So when we compute for instance, when we compute different loops and so on, we have to give initial conditions. So the initial conditions in matter domination was also from general relativity. So the whole analysis is more or less consistent with general relativity because it was designed to be like that, because we're still improving on the methodology. So basically, this methodology of going beyond lambda CDM is very prone to systematic effects, because the analysis in lambda CDM is already prone to systematic effects. So we don't want to be very bold already in year one. But yeah, I think that it was decent enough, the perturbative template that they used. So yeah, to use perturbative templates because they're limited in scale dependence. So perturbation theory, it's not something that allows us to go beyond perturbation theory. So it's not non-perturbative. And but we already have some idea and some methods that give us the result in a non-perturbative way, which is precisely using n-body simulations and different methods that are similar in spirit as of n-body simulation. But as we can see already at when we compare the equations of motion that we need to do in one side and the other, we see that there's way more complexity involved in the n-body simulations avenue. So basically we have on the left-hand side, we have a fluid description. Basically, we were just going to evolve CDM as a fluid. On the right-hand side, we're going to evolve 10 to the 8 particles of dark matter. So basically, this is a more intricate and complex analysis than using just linear theory. So as I said, cosmological simulations, they use 10 to the 8, 10 to the 11 particles in a cosmological size box. So basically, cosmological size box means that we need to be at least a little bit close to the horizon scale, which is around 1 gigaparsec. This is a lot. And this is very much time consuming and computationally expensive. And the strategy that we use to constrain models is the same as we have been doing in the past decade with in cosmology. We do a Bayesian inference, we use Monte Carlo Markov chains, and we have to sample a very big number of points in the parameter space. And this parameter space is going to be enlarged in the case of beyond lambda CDM models. So there is an obvious shortcoming, which is just prohibitive to run 10 to the 5 simulations, at least in lambda CDM, for instance. So basically, we don't want to do that. We don't want to just run n-body simulations for each point of the parameter space. We want to do something better. There is one method in n-body simulations that is computationally less expensive, which is this one that I'm going to talk about, which is the particle mesh algorithm, in which we just don't solve directly for the force. We don't have a lot of, since we have a lot of particles, basically when we compute particles forces, we're going to do this in a complexity that scales with n to the 2, okay? A particle mesh code, since we're going to place these particles on a mesh grid, we're going to reduce the complexity and just use the bottleneck of the complexity will be the same of performing a fast Fourier transform in the number of grid points of your mesh. So this is good for, especially for modified gravity and theories like that, because it's cheaper to run, but it also has its shortcomings. Since it's a finite grid, so we are not going to use any adaptive mesh grid. We're not going to use any more intricate way of computing the force between particles. We're just going to get a grid and subdivide it. There is a finite grid problem. We lose resolution, and then we need to increase resolution. We need to make it thinner and thinner. And this has a bottleneck of just using more memory because FFTs are very costly to do. So we lose accuracy at small scales. So basically, for beyond lambda CDM, we always have in mind the trade-off between time and resolution of what we want to do. So an even faster approach is precisely the one that I'm going to talk about, which is the co-moving Lagrangian approximation. It's just a method that will reduce the number of time steps that a normal n-body simulation will have to take. So it combines LPT, which is Lagrangian perturbation theory, with the particle mesh algorithm for small scales. Essentially, what this means is that instead of just running a simulation in the usual way of thinking of Eulerian time steps, we're going to go to a different frame where we have this Lagrangian frame, where we're going to add already the displacements that we know analytically from Lagrangian perturbation theory. And we are going to solve the small scales physics to the best that we can using a particle mesh algorithm. Okay, so this is.
You said, so you lose resolution on small scales, right? But then you have like baryonic effects, you have a lot of different effects. So is there a consensus on how much is necessary, or and the rest it's useless to refine the resolutions there?
So maybe I can talk more about this in the end, but basically, when we have, there's a consensus of the size of the simulation that you need to run to have good and accurate predictions for the metapower spectrum, at least, in which you will not go beyond k equals 3.14, for instance, which is not where we expect to see baryonic effects and baryonic physics. But at the same time, we need to go beyond because we need to compute integrals that they have support on very small scales. So we need to deal with baryonic effects as well. And this is not something that I at least have worked on, but I can talk about some avenues there. So in the end, with COLA, we have we reduce the number of CPU hours, wall clock hours, by at least a factor of 2, which is very good. And due to the many different numbers of theories that we have in beyond LCDM models. Okay. And this is just a comparison that we did for the Euclid collaboration, in which we compare different codes that have modified theories implemented already. And we can see the MG COLA predictions, which is COLA simulations. They are always at least in the bottom of this plot over here. This plot is, of course, very unintuitive because to make a very good comparison between codes, you need to run them on the same in the same place, a machine. Thank you. The same machine. So this was a combination of different machines, but we try to do our best to more or less showcase the results. You can see, of course, there is no point of using COLA if you just want to use lambda CDM for this specific target, which is computing the metapower spectrum. because we already have very good codes like PKD Graph 3, which is designed to run on GPUs. So it has way more capability of finishing the simulation faster than any other of the codes there. So yeah, this is the comparison, and we have shown and the claim that we often say that Cola can be faster than the other ones.
So in this case, you're targeting one specific accuracy on the matter power spectrum, and they all reach the accuracy.
Yeah,
Okay.
that's the thing. Yeah, this is a very. This was a requirement by the collaboration, but this is a very unfair assessment. But I can show, I can discuss all of the caveats. So for this, we were aiming to go to cable 6. Yeah, so we were using a very small box for this, and we had to increase. So these MG Cola points over here, they are even more expensive than a normal Cola simulation. So for instance, these ones here was using a very thin mesh resolution, which was like 5 times the number of particles. Okay, so even for a Cola simulation, this was already very expensive, but still we were the costless one.
So all the codes agree at Keiko 6, say at the percent level?
Yeah, I'm going to show this is just the comparison that I wanted to show the cost of doing these simulations. I can talk about, so the baseline of the comparison was MGRepo, which is the newest version of it's Gadget 4 plus a different galaxy formation theory model on top of it. So yeah, so why is it so hard for me to present these seminar in a non-technical way? And why is it so hard for us to do modified gravity and go to nonlinear scales? Basically, when we have theories, so when we have to run a simulation, in general relativity, we just have to solve 2 equations in a very non-trivial way, as I showed before. But we only have to solve the Poisson equation and the geodesic equation. So the first one and the last one. So the first one in general relativity has that beta phi function there equals 1, and that f function is just 0. In modified gravity theories and some other theories that can be cooked up, because we all know how theories love to cook up things, the equation for the scalar field fluctuations is nonlinear by itself. So we cannot use regular solvers. So generally, we're solving the linear Poisson equation, but at the same time, we're running a different grid where this grid is using an adaptive mesh refinement code, so algorithm. So this is very costly to run a simulation. So when we do one time step in general relativity, we're doing a lot of time steps in modified gravity. So this is very costly. So basically, when we talk about modified gravity.
Can I just go back? So the last equation, it can be changed also if you have fifth forces, for instance. Is that easy?
Yeah, so I'm also going to talk about that, but the fifth force comes precisely because of the Poisson equation. Because that beta phi there will be a general relativity part inside of it, plus corrections coming from different theories. So the fifth force will appear as just general relativity plus the potential of some weird function coming from modified gravity.
Okay.
So yeah.
Yeah, going back to the comparison of the codes, you're saying that we will use the power spectrum, the small box as your metric, right? As
Metric?
You have to reach certain precision, right? And then you compare the time.
Yeah.
So can you also compute the bispectrum with the code, and
So
they also compare favorably?
yeah. That's the thing. Like there's a lot of so to the level that we are in stage 4 requirements, and a lot of the analysis that the Lambda CDM community does, we are not going to be fully able to do it in beyond Lambda CDM because there's a lack of people power, there's a lack of CPU hours that you can have access, and so we have to do our best with what we have. The matter power spectrum is a standard one, and we need to use, for weak lensing, for instance, we need to do 3x2. So we do matter power spectrum, and then we need to do galaxy power spectrum. For the bispectrum, I don't know if it's the best way forward with modified gravity because there's a lot of mode coupling already at the normal general relativity and normal physics. So it would be very intricate to do, but in principle we can. And we have these data there, so anyone can. I don't know if anyone can play this, but we can. We definitely can try to run simulations and check that.
You can even compare at field level, right?
So field level is cheaper. So field level, that's why I also going to talk about in the end, because field level, basically, so field level on the density field, not field level on the maps.
No,
Okay.
that's-
Yeah, the maps is way more hard. But on the density field, it's way cheaper to do in modified gravity because it's just LPT. So we can just do 1, 2, 3 LPT. There's a lot of room to explore and go forward. That's because it's way cheaper than do anything else that requires these projections and so on.
So just a curiosity on spot. Do Euclid emulator have a fine graph?
So no, Euclid emulator, it has only lambda CDM and W0 WA WCDM. And it's not here. So the simulations from Euclid emulator 2 would be this point here.
Okay.
It would be BKD graph. Yes. So now just a brief review. Modified gravity, the most general, fully second order equations of motions with just one scalar degree of freedom on top of the metric one is the Horndeski gravity. It has these different couplings that are non-renormalizable. They're ugly. They're everything like that. But after GW 0817, a lot of them died. And we just remain with 3 functions. So this is basically the function that will give the kinetic term of the scalar field. So it's just going to be phi nabla phi squared. This is a term that interacts, is like interactions of the scalar field with itself. And the last one is a conformal coupling with the metric. Okay, usual FFR things and stuff like that. Okay, so much of the complexity has vanished. And we hope that more of it can come from other ground-based detectors like ET and Cosmic Explorer, which may be picked up by LISA and the ESA and the counterpart in the US. So modeling of these theories at the nonlinear level remains very intricate because of that equation that I said that is nonlinear. And now I'm going to discuss why there is this nonlinearity in these equations. So basically, we have just 2 nonlinearities. So the aim of this slide now and this part of the talk is to say that even though modified gravity has a theory, has a model, some of the theories that we use can be already also used to test agnostically the growth of structure. So basically, nonlinearities in potentials will generally arise because of we have a theory that is scale dependent. The growth is scale dependent. So if you want to bin the growth factor, you can use some of these simulations that we have from nonlinearities in potentials. And we have the other type of nonlinearity that is nonlinearities in the kinetic terms. This is just scale independent theories. So basically, if you want to test the growth rate of the universe in a way that is agnostic, like binning and so on and so forth, you can just motivate your theory and use some of the simulations that have only a scale independent growth. So the nonlinearities in how we need to deal with them in very high dense environments. Basically, we know that general relativity is the correct gravity theory in very dense environments. So these theories that have this nonlinearity in potentials, they are tuned in which the potential is something that is more or less like this in very dense, very high dense environments. The effective potential asymptotes to the density one, to the one that is multiplied by the density, and in very low dense environments, we have that it's a very flat description. Okay, so this is just a tuned way of killing the fifth force that arises in very dense environments. So basically, we have a screen force. So the field is dead in this type of nonlinearity. The field is effectively dead. And then outside of this thin shell that is dead, it can go back up and evolve, okay? So the fifth force in very dense environments disappears, and in cosmological scales, it can still act as dark energy. On the other one, we have nonlinearity in the kinetic terms. It's a little bit more intricate to understand this one because the field is not dead. So the field is alive, the field is evolving, the field is not in a constant configuration, but the fifth force simply disappears because we have that this term over here is going to dominate on top of the other one. And then in very dense environments, we disappear the fifth force. Okay, this is usually called the Weinstein mechanism, and it has more or less this scale dependence. So basically, we will have a cloud that is given by the Weinstein radius. We have the Schwarzschild radius of the theory, and we have the mass scale of the theory as well. Okay, so this is how we the nonlinearities in kinetic terms, they disappear at small scales. So even though this is more or less theoretical and complex to understand, this is just something that we already know how to deal with. So basically, going back to the paper that we did for the Euclid Consortium, we compared the two theories that exhibited these two nonlinearities. So basically, we here compare an FO4 theory, which is just a theory that exhibits this scale, this growth that is scale dependent. We can see that at linear scales, there is already something rising. So it's not just an amplitude shift. So basically, this just shows us that the growth is scale dependent. And we can see that MG Cola and all of the other codes that we show here, they are in agreement up until 10, but the cutoff scales was around here. Okay, they were in between 2% in all of them. The same thing with the modified gravity that shows scale independent growth. So contrary to the previous plot that I showed, we have that we don't have that scale dependent feature at linear scales. We just had an amplitude shift because we were boosting up the modified gravity, the Newtonian potential at large scales. So basically, we also get a little bit worse on these comparisons here, but MG Cola, once again, is tuned and is also in agreement with all the other codes. Yeah. So let me just see how am I in time. Yeah, so this part is just...
Is there a reason why all the models, they enhance gravity at small scale?
It's just because of the theory. We can
You can change the parameters and then...
Yeah, well, you can just choose another theory. It's just, this is just a comparison on how we deal with nonlinearities. We're doing good. So basically, if you just have a different theory that is not enhancing, it's suppressing, we can just use the same things, the same codes that we have here, and they will all be in agreement. It just depends on the something that the person is going to choose.
And the codes include the screening mechanisms that you show.
Yes, so COLA also includes something that is even faster because we don't solve for the other equation. We just use approximations that show that we are in agreement with codes that solve that equation. So MG Arepo solves that equation, and we show here
The
that
third equation, the equation of
the Klein-Gordon one.
the Klein one.
Yeah. So yeah, they're more or less in agreement. Yeah, and just to finish this up, it's just that the same effort that we did when using and validating COLA and other simulation codes, we also need to do at the level of doing Bayesian analysis to see if these codes, they behave well around the parameter space. And basically, we did that very recently with João, Vivian, and Jonathan Gordon, now a PhD, now a doctor, PhD student from Vivian, that we precisely designed an experiment to see if COLA was actually performing well when we had to do precisely like a stress test of the methodology that we had to design. So basically, we just chose one beyond-LCDM model, which is WCDM, and we wanted to use and compare it with Euclid Emulator 2, and then we just created an emulator to see how well the Cola predictions would be when we have a very large box to sample from. So the strategy was to not emulate directly the boost, because the boost from simulations, they are very noisy, precisely because we have nonlinearities in the BAO scales where we have that it's smeared and so on. So basically, we instead emulate that quantity over there, which is B bar. And we can see that our strategy to Cola is not to say that Cola or other methods are designed to create an emulator from scratch, but rather to extend current emulators to different modified gravity theories or beyond lambda CDM theories. Precisely what I said, when we just take this ratio here of 2 Cola simulations, what we are left with is just a noiseless prediction that I showed here. The difference at small scales is just because we're comparing two different cosmologies. But at large scales, they're more or less tamed. Okay.
This is lambda CDM, right?
Yeah, this is WCDM.
WCDM.
Yeah. And also we, as Rogério said, we tested 3 different scale cuts to check for biases with our method and Euclid emulator too. So the first experiment was to use something that we have developed in the past, which was to just add 1 reference point here. So just use this equation here once. And in the end, it was not good, not only at the level of the power spectrum, which we see that we were disagreeing at 6%, even above at small scales. And when we did the full analysis, we see obviously that the Cola was not able to recover the fiducial data vector if it was not directly on top of the reference of where we trained. So if we have a data vector that is very far off of where we have trained, we were simply not able, and Cola was not being a good method to use. However, we changed our strategy to first accommodate a very large number of reference points. So basically, instead of just using once, that the ratio between Cola simulations, we used a lot of them. The results improved. They are these 2 here, where we used 101 reference points. The results were now on the level of the matter power spectrum to 4%. But what really improved was when we just jumped directly and used a subset of for each beyond lambda CDM prediction, we would now have the same prediction in lambda CDM. So basically, we have for every beyond lambda CDM theory, we can always get the cosmological parameters and just create a prediction for lambda CDM on top of that. Okay. And when we did that, it was amazing because we really reduced the discrepancy that we were seeing before when we just were considering the same beyond lambda CDM model ratios. So when we see here on the bottom, we have 2% at k equals 3, for instance. And this is for very fast Cola simulations. So checking for biases using different cutoffs, we see that different cutoffs, the strategy of using lambda CDM references in a very large number improved. So basically, we had almost no difference when we did our parameter inference. All of the predictions here given by the stars, they are very much on top of where the fiducial data vectors were. And the chi-squared test was more or less okay. This was performed by João. I think I have it wrong there. So the difference between the chi-squared from E2 and Cola was smaller than 0.2, not 2, okay, 0.2 for this C2 cutoff here. So basically, if someone is to use Cola to do an analysis of a beyond lambda CDM model and follows our scale cuts and our strategy, the result is expected to not be biased, okay, given by our analysis here. So of course, there's a lot of things that we didn't consider, like intrinsic alignments, baryonic feedback, and so on. So, but in this first experiment, we were very happy with what we get in the end here.
Did you use a neural network, right? To look at-
Yeah, we use different, the emulators were created in using different approaches like neural networks, PCE, which is both the same method that Euclid emulator 2 uses, and Gaussian processes. They all were all in agreement. So the results that we showed here, it's also irrespective of the emulation method that you choose. So it's insensitive.
And how many simulations you need for the training to train the emulator?
Yeah, so we needed, so better than the number of simulations, it's better to give the number of CPU hours to run and train, which was 10 to the 5 CPU hours, while Euclid emulator 2 took 10 to the 7 CPU hours. So the same claim that we have that in wall clock, we reduced in 2 orders of magnitude. We also had when we did the simulators. So it's also something that is good. We keep on hitting the same things that we expected.
And so this is for lambda CDM, right?
So this is for beyond, no, this is for WCDM.
Ah, it's CDM.
Yeah,
There's a typo there.
there is a typo there. I'm going to fix it.
And how do you expect this to change if you go just one parameter more, say down to 0 WA?
We're actually checking this now, varying W0 WA, maybe the mass of the neutrinos. I don't expect it to change that much because W0 WA is easy to handle. Scale independent theories should be more or less okay. Yeah. So what I want you guys to take away from this talk, which was an amalgamation of different talks that I have given in the past. I started very broad, and then I talked about specifics of simulations, and then theory, and now statistics. So it's in the end, it was just to say that to set the ground that in the beyond-LCDM community, we need to know better the specification of surveys and target what we want to do. Basically, the simple analysis that are better for us to handle with, like the ones from DESI that people just release some analysis. So for weak lensing, we also expect to deliver some good methodology that we can trust. COLA can be one of the approaches to do this. There are other approaches, of course, not a lot of them. Yeah, basically, this is just cosmic shear. So this talk, I just talked about cosmic shear and emulating the matter-pore spectrum and simulating the matter-pore spectrum, like estimating the matter-pore spectrum. But we know that in photometric probes, so when we do galaxy surveys using photometry, we also have the position of galaxies. And to do that, that is going to be a little bit more intricate because N-body simulations, they just evolve particles and not directly the galaxy. So we don't know more or less. So we still need a prescription to populate our simulations with galaxies. And basically, we need to see if these prescriptions that are used in lambda CDM also are valid, or they also work. The fits that people use for HOD and so on, they also work for these theories of gravity. Or we can also use different approaches like the ones from Bacco and Emilus Heft, that this combination of hybrid effective field theory, which combines Lagrangian perturbation theory with N-body simulations. So this can be more agnostic and easier to do for beyond lambda CDM. Yeah, so that's it. I'm hungry.
Okay, so the idea is to come back at 2 p.m. and then have a discussion on the different methods to handle nonlinearities and also galaxy bias and fast simulations, slow simulations, and EFT. What is it? Uh-oh. Anyway, so we come back at 2, okay? And we start discussion at 2. Maybe Nikki will be here, not sure. Okay, try lunch. No? No.
Mas vai que